Our project is called Mobile Web Acceleration via Reliable-UDP with bandwidth estimation. Our group members are Xu Ming, Zheng Jiekun, and Wang Jianan. First, there have been many approaches for mobile browsing acceleration. The first one is on application layer. Some well-known projects such as Speedy protocol has been done. The second approach is on transport layer. Someone tried to modify TCP and someone tried to write IUDP to support better function. And in our project, we have designed and implement a new IUDP protocol, which has following features. First, dynamic rate control algorithm based on bandwidth estimation. And our protocol is more resistant to bandwidth fluctuation and disconnection. And it can achieve higher bandwidth utilization in Wi-Fi mobile network. During our project, we have used the following development tools. The first one is Android App Development SDK. The second one is Java Eclipse IDE. The third one is Java Runtime. The last one is Bitbucket. We use it for version control. In the first semester, we have built up a mobile local remote proxy system. By the end of last semester, our system supports TCP transmission and UDP transmission. And in this semester, our main work is on incorporating IUDP transmission into our system. And as you can see in the picture of overall of our system, we have the three yellow modules indicate the IUDP modules that we have added. The first one, we add a IUDP module at the local proxy site. And this IUDP module will receive HTTP request from the browser and start IUDP transmission for this HTTP request with the remote proxy. And we have a selector to coordinate all the underlying HTTP and IUDP transmission pairs. At the remote proxy site, for each HTTP request, we have a receive thread and a send thread. The sending thread is responsible for fetching the web content and send the web data back to the local proxy. And the receiving thread is responsible for receiving ACK segment from the local proxy and update the retransmission stack for the sending thread. And we also add a logging system for our data analysis. And the format of the logged data is system time of the received packet, sequence number of the packet, data size of the packet, and the current ACK. Now let's come to the protocol design of our IUDP. First, let's have a look at our IUDP header field. Our IUDP header has 16 bytes of fixed size and 8 bytes of optional size. And we have two types of segments. The first one is ACK segment and the second one is data segment. All our controls are based on information provided by the IUDP headers. And our IUDP support reliable transmission. We added the ACK acknowledgement into our IUDP to support reliable retransmission. And in order to improve the retransmission efficiency, we use selective repeat with the help of a stack header field. In this figure, we shows basically how ACK and stack works. The ACK indicates the packet number of the next packet that the sending thread should send. And the stack field indicates the packets, out-of-order packets that the receiver has received. So the sender do not need to send the packets indicated by the stack field, and it only need to send the packet indicated by the ACK field. The next feature of our IUDP is called fast retransmission and adaptive timeout. For fast retransmission, we add this feature to accelerate advancement of ACK value, and the retransmission is triggered by the triple duplicate ACK, and is faster than triggered by timeout. We also adaptively compute our timeout value to improve the responsiveness of our IUDP. And the timeout value is based on average and the variance of the past timeout values. And this can help us balance between transmission redundancy and retransmission responsiveness. All the past features are based on well-developed TCP features. And for the congestion avoidance, we use a different approach from TCP. TCP detects congestion based on packet loss, and we avoid congestion by adjusting sending rate based on estimated bottleneck bandwidth. And the estimation of bottleneck bandwidth is inspired in our system is inspired by an existing end-to-end bottleneck bandwidth estimation, and the principle is as shown in this figure. Suppose there are three links during the transmission, and the bottleneck link capacity is C, and the other capacity are 3C. Suppose the initial gap is L over 3C, where L is the packet size, and in the bottleneck link, the gap will be enlarged to L over C, which is 3 times of the initial gap. And when the receiver detects this kind of enlargement of the gap, it can calculate the bottleneck link capacity based on the initial capacity, the receiving gap, and the sending gap. And we can see it can easily calculate out the link bottleneck capacity, which is C. Okay, this basically all about our protocol design. And in order to test the performance of our protocol, we design some experiments, and what we want to know is first the performance of IUDP at different stages of transmission. The performance when the network has congestions, the efficiency of our IUDP transmissions, and the performance when network has fluctuations and disconnections. And we also want to measure the responsiveness of our rate control mechanism to changes of network conditions. And this image shows the setting of our experiment. We have a laptop, which is a local proxy, and it sends a request via the wireless network to remote proxy, and the remote proxy will fetch the web data from HTTP server over a wired TCP, and then send the web content back to the user. And in the wireless transmission, we switch between IUDP and TCP, and to compare the performance of these two protocols. To eliminate the effects of external errors, we automatically run the testing programs in each condition for 10 times and calculate the average performance from the logged data. And we also simulate different kinds of network conditions, such as the squeezed available bandwidth, and we achieve this by injecting traffic into this wireless network using NetProbe tool. And for the periodic disconnection, we periodically disconnect the Wi-Fi connection for 20 seconds, 15 seconds, and 5 seconds, and then reconnect the wireless network after a 0.5 second pause. Now let's come to the experimental results of our testing. This figure shows the good put of IUDP and TCP in different for different file size. We test on file size of 300 kilobytes, 600, 1 megabyte, 2 megabytes, 4 megabytes, and 6 megabytes. As we can see, for file size of both small and large, IUDP can achieve a higher good put than TCP. So it means our IUDP is better than TCP in different types of web content transmission. This figure shows the good put of IUDP and TCP when the network suffers from bandwidth fluctuation, and we test the performance with different size of fluctuation. As we can see, the IUDP can achieve better good put than TCP when the fluctuation size change from small to large, and which means when and we expect that in real mobile network, when the fluctuation happens, our IUDP can perform better. And this figure shows the good put of IUDP and TCP when the network have different available bandwidth. And as we can see, in network with different bandwidths, IUDP can achieve a higher good put than TCP. And you can see the good put of TCP decrease linearly, but the IUDP decrease slower than TCP. So it means in network with different bandwidths, IUDP can achieve a higher good put. And we also calculate the retransmission redundancy for IUDP in network with different bandwidths. And as we can see, the redundancy is around 5%, which is acceptable. So it means our retransmission do not waste too many web network resources for the reliability. In this figure, we shows the good put of IUDP and TCP when the network has a disconnection, and also the IUDP has a better good put than TCP. And the reason may be when there is connection, TCP will just cut its sending rate to half, but our IUDP will not decrease the sending rate that much. And we also check the sending rate control for the network with disconnection of 15-second period. And as we can see, the yellow line indicates the sending throughput at the sender, and the blue and green line indicates the throughput and good put respectively. And when there is a drop of the good put, it means there is a disconnection, and we can see that when there is a disconnection, the sending throughput will drop, which means the sender estimate the available bandwidth, and it's very small, so it's control its sending rate to a small value to avoid the congestion. So it means our rate control can quite accurately detect the network changes. So based on this experiment results, we can conclude that our IUDP has better performance than TCP, and it's more resistant to bandwidth fluctuation and disconnection. It has higher good put and bandwidth utilization. So we have our future directions may be to adaptively and control system parameters to generally suit different network conditions. We may optimize existing algorithms as well as integrating other possible efficient algorithms. And one more thing important is that we really need to perform testing using mobile phone and 3G, 4G network to support the usability of this IUDP in real mobile network. So that's all about our project. Thank you.